Devendra Duredi. He's a principal software engineer at Mellanox Technologies, which has been recently acquired by NVIDIA. Devendra was instrumental in building the several key technologies like SHARP, UCX, HCall, etc. Previously, he was actually a software developer at OSU and worked on the design and development of the MHAPIS project. He has received his master's degree in computer science and engineering from the Indian Institute of Technology, Kanpur. His research interests include high-speed interconnects, parallel programming models, and HPC and DL software. So let's welcome Devendra.
Thank you, Dr. Panda.
Yeah, can you please share your slides?
Yeah, let me share my screen. Let me know if can you see my slides?
Yeah, but it is coming in the presenters mode. You can display like the two slides are coming. So you can.
Yes. Perfect. Yeah. Okay. Thank you. Thank you. Thank you, Dr. Panda. So today I'm going to present the SHARP in network technology from the Mellanox. Now it's NVIDIA. So that SHARP stands for Scalable Streaming Hierarchical Aggregation and Reduction Protocol. Let's dive into it. So before moving into more details, so first the question is, so why do we need a efficient in-networking computing? So if you see the recent trends in the data center technologies, so I have put together, collected a few trends from different areas. So the first one is the Moore's law processor technology. If you see the per core processor speed, so it's not going to double every couple of years anymore. It's reached a kind of a peak. It's now people are moving towards the different kind of system architectures where they combining CPUs with the GPUs to overcome some of these challenges. So this increased system complexities is posing more, more challenges to the in many areas. The same way, if you look at the kind of networking Moore's law, if you observe Mellanox technologies for last couple of years, for every 2 years, there's a kind of bandwidth is doubling. This is nice. And for last few years, the latency also came down off for every new generation. This is nice, but now we reached a state where latency, it's kind of hard to cut it down by off for every generation. If you look at the current switch latencies, it's kind of 100 nanoseconds. It's not going to be 50 nanoseconds for the next generation and 25 for the one after another after the next one. Even the point-to-point, it's kind of 60 microsecond. It's kind of it's very hard to cut down anymore the latency side. And if you see the data growth, as we know, data is exponentially growing because of the trends in the technologies. And if you see the DL models, they are getting bigger and bigger for every every year. There are more parameters, more data, and so to combine all these, we need a faster interconnect for sure. So if you ask the question, is fast is enough? May not. So we need a efficient interconnect where it understands the data and take the holistic approaches and in the overall system design. So in Mellanox so in networking computing, so there are few technologies I would like to talk here. The terms I'm not defining here, but it's kind of approaches we follow. So the offloading and co-designing and in-network computing. So the offloading, I mean, uh, it's nothing but offload your work to somebody else. So so here we are moving most of the functionality from the CPU to the network. So this is the core technology for all the Mellanox uh, uh, networking components. So it's RDMA is a key and efficient feature to offload work from CPU to the NIC. So if you see the core designing here, we are trying to rethinking what should be the boundaries between the software components and the hardware components. So what part of the things should we run into the software, and what part of the things we can move into the hardware. So we are constantly, I mean, challenging the hardware. Can it take can it offload? Can we move this functionality to the out of the node? It's it's not only the end node. So we are even thinking like moving towards the network switches and the fabric uh, to make the efficient approaches. So the in-network computing is nothing but a type of co-designing. So I will, uh, uh, it's to move traditional compute operations to into the fabric. Let's go into in details here. So the first offload in networking compute technology from the Mellanox is the co-direct. Uh, so so if you see the any network operations, you have a like send operation to send data from one source from one source to the another source. Similarly, you have you can have an operation to receive data from the specific source or multiple sources. Uh, when you are implementing a collective operation you can actually, there is a dependency between all these operations. So for example, if you see it here, I just put it a ALLREDUCE operation. So one way you can do is every process can send data to one process. It can compute and it can distribute data back to the everybody. So, but this is very inefficient because in terms of congestion, because one source is receiving data from everybody. So it's very inefficient. So you can have a better algorithms like recursive doubling and ring-based algorithms where you can have a logarithmic uh, 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 complexity algorithms. But the problem here is it has a multiple steps. So you have to receive the data from a specific sources, and you have to send the data to the a multiple destinations. So, but so the approach here in CoDirect is, so you can create a dependency graph here. So and you can the dependency you can offload it to the hardware. So otherwise the CPU has to involve to process every send, and then move into the iteration, then wait for the all the wait for the data from all the sources, then do the computation and deliver it to the next hop. So instead of host involving in these steps, so what you can do is there are there are two operations, I mean, there are two work request opcodes, the wait and enable. A specific, then when you post the send operations, and you can say you can insert a triggers like wait for completion of the send operations before executing another work request. So with this approach, dependency graph approach, basically you can offload all the communication to the hardware. For example, here, let's take a rank 2. Here, this has to receive the a sum from rank 0 and a rank 3. And then it has to do the summation here. Then it has to send the rank 5. So basically, you prepare the sequence of operations like two receives followed by a wait operations, then you then a send operation. So then you switching all this stitching all these work items, and you post it to the hardware. Then the hardware will execute independently.
So
So
Deva, I had a quick question.
mm-hmm.
So what is the size of the reduction operations that can be performed with the latest adapters?
It's an INFINIBAND size. It's I mean, it can do.
No. What I was trying to say is like what message sizes? Like earlier, like several years ago, only
Mm-hmm.
do like up to 64 bytes of reduction on the adapter. So has that size changed now?
I think it's MTU size now.
Oh, it's MTU size. Okay, that's good. Thank you.
I can recheck for you that.
Okay, thanks.
Okay, so all this is happening at the end node adapter. So now the next technology is and the SHARP. So I mean, it's another in networking computing technology from the from Mellanox. So probably you might have seen these slides from earlier Mellanox presentation. So just the approach here is the earlier it's the left side, it's a CPU centric. There's an onload network, I would say. So here you must the compute engines are your CPU and GPU. So these components, these processors have to wait for the data before performing any operations. So this will become a bottleneck for the performance. So in the right side, in the data-centric approach, so if you see whole system, while the data is moving into the fabric, you can do a efficient efficient decision whether what to do with that data. So if you analyze the data while it is moving, so you have an opportunity here to improve the things. So so let's see. So as earlier slide, I said that it's very hard to cut down the point-to-point operation latencies. So how can we improve overall latency of how we can improve the efficiency of the network? So here it is basically, if it is a CPU centric and if there is an operation, if your end processor has to involve in the processing the data, so there might be there is a bottleneck. It has to wait, it has to process, then it has to go through the multiple steps, iterations of the data. So it's a order of tens of microseconds. So whereas in the data centric, while if you can take the decisions while data is moving in the fabric, so that there is the opportunity to take a better data analysis. So this will cut down the latencies to tenfold. So then you can you can increase the efficiency of your fabric. So yeah, the traditional collective operations, these are patterns, tree-based patterns, many to one, one to many. So it's not a good solution for the large data. So it requires the higher trees, larger radix, and the algorithm has to go through multiple iterations. So there is a noise, there is a possibility of congestion and a noise at the node level. So all this will increase the latency of the operation. So if you take the example of recursive doubling, uh, so each rank is in the there is a log n steps in the algorithm, and each rank is talking to the I mean the logarithmic a for rank in each step. Uh, it's sending and receiving, and it doing the computation. Then it is there is another phase to result distribution. If you see the overall data, uh, so the data is traversed twice in, I mean, for X amount of bytes, but there is actually 2x amount of data is traveled in the fabric because of the algorithmic nature. So there is twice the bandwidth is needed here to perform this operation. So what we can, how we can improve the things. So the in-network tree-based aggregation. So while data is moving into the fabric, so I mean you do the computation while moving. So if you see the traditional algorithms, they are suffered with the bandwidth at the end node side. Uh, so I mean, end node can receive only the maximum bandwidth it can get from that adapter. So you can improve the things by having a multiple adapters, okay, multi-rail, but still, but if you see at the switch has a very high bandwidth. It can receive the data parallelly from multiple end nodes. So it's kind of a very high, the problem you can do, I mean, now you are doing a computation in the order of one instead of a order of n nodes. Uh, so while data is sent from the out of the host, so the switches can aggregate the data uh, and they can move data to up in the fabric. So when they have the end results, the data can be distributed back to the back in the fabric tree. So if you see it here, the data is traversed only once. You sent the data to the fabric and you got the result. So there is no, the end node does not have to go through the multiple steps of the algorithm, and you cut down the amount of data, and it's very scalable because the most of the while in the leaf level switch, while one switch is doing reduction, the others all the switches in the same level is doing the computation in parallel. So once they uh, then they are moving the data to the upward. So it's highly scalable. So if you see larger supercomputers, the most of the networks are level 3, level 4. It so I mean it's very efficient to do the computation in the fabric here. Uh, it supports the multiple outstanding operations. It's not that only one operation you can send to the fabric. It can post multiple operations outstanding, and it helps for both the HPC and deep learning frameworks. We'll go in more details in the next slides. So it supports multiple type of operations: barrier, reduce, all-reduce, and broadcast, and many more are coming in next generations. And it also supports multiple compute operations like standard MPI compute operations like sum, minimum, maximum, minimum location, max lock, or XOR, all logical and bitwise operations. And it also supports integer and floating point, and in floating point you have FP16 support as well. So the SHARP is evolving, and it is a now second generation SHARPv2. The first one was the switch IB2, the EDR INFINIBAND switch IB2. It was only supporting the smaller message reductions. We were referring it as a low latency trees. It is very latency optimized. You fully offload to the switches, and it's asynchronous. The next generation, the HDR quantum switch added a support for the larger vector reductions. We are throughout this talk, we're referring it as a SAT, stands for Streaming Aggregation. It is a bandwidth optimized, and it's also fully offloaded and asynchronous. So just what kind of performance you can expect from this from the SHARP. So here this is low latency trees, smaller messages. If you see the left side, it's on a 128 nodes compared for the 8 bytes and 128 bytes. The solid lines yeah, sorry. Yeah, the solid line is the SHARP numbers, and dotted lines is the host based. So here, the host base also is very optimized. I am not saying that it's bad. That is also that is very optimized implementations. But the thing with the hardware offload with SHARP is you kind of get a constant latencies. If you see, there is a small jump at the 60 nodes. Probably it's a multi-level because it's multiple switches at the leaf level. So then you have to have a 2-level tree. So then you will add up a switch latency here. It's 100 to 200 nanoseconds. So then again, that's once you reach there, then you have a constant. So then you might have another couple of hundred nanosecond latency addition for the if your fabric is going to if your uh, reduction tree is going to be a 3-level. So that is the kind of advantage with this with this. The right side is the large scale we ran at University of Toronto. We just validated that the latencies are very low and constant. So what the SHARP new features in 2.0? As I said, it's a HDR quantum switch technology. So it still supports it. I mean, we enhanced the small vector reductions LLT. The additions mainly earlier there was the small packet size was limited to only 256 bytes. That is increased to 1K here, 1 kilobyte. Each send has to be in the order of the maximum LLT packet size. As I said, it is asynchronous, so you can post multiple fragments, but the fragment size is improved from 256 bytes to 1 kilobyte in the HDR SHARPv2, and and also improved the latencies. And the major one is the support for the large vector reductions. This is performing reductions at the line rate. So this is we call this as a streaming aggregation trees. Currently, we support 2 simultaneous streaming operations per switch. So it's a limited resource. In the next generations, it's going to be remove these limitations. But currently, in parallel, you can do the 2 simultaneous streaming reductions per switch. And the streaming reduction is works with in conjunction with the GPU direct RDMA technology. This is a the SAT technology is a killer app for deep learning workloads. We'll do more in the next slide. And also the 2.0 is added the initial support for the broadcast. there is a, I mean, for the end of the year release, there is improvements in the bcast, but it's currently supports the through API. You can enable the bcast as well.
So just a quick question, Deva. So you mentioned SHARP supports GDR. So can I pass like a device buffer directly to the SHARP APIs, and would it work automatically?
Yes. Yes.
Okay.
Yeah.
Thanks.
Some more new features are we added support for virtual ports to enable this technology in the clouds. And also we added a UCX backend for the daemons communication in between the SHARP daemons and SHARP AM. And it was supporting only earlier the default P key. Now we can use the non-default P key as well. And also added the PCI relaxed addering for to enable the performance in cloud environments. So the SHARP design characteristics, if you see the reliability model, so you natively have a transport level reliability, but it's it's possible that you can have a wrong operation posted to the fabric, like mismatched length, mismatched operations. One end node might be asking a some operation, but some other source might, if it is the tuple is not matches, like what type of operation you are posting, what how much size. There is a possibility that error can happen. It's very easy at the software layer to deal with this, but in the hardware layer, so we improve things. I mean, so the tree failures is detected, and it automatically revokes the resources. It notifies the end nodes that type of the error happened in the fabric. Then the software can take a decision whether to wrong in the operation, or is some other reasons. They can fall back to the software schemes. So as I said, the new the other the design considerations is it's a scarce resources, and the SAT tree is mirror to the low latency tree, but it is completely different tree. So it has a different limitations and different protocols and different way of pipelining the things in the fabric. So so as we know that you can do a certain number of streaming operations in the switch. So how can we design the network efficiently for the SHARP? So this we are calling as a rail optimization for the SHARP. So for example, rail optimized design topology properties. So you would like to keep the rail affinity connectivity. That means a rail from each end server connected to the same leaf switch. So for example, if you see here, two port server, on the left side, two ports are connected to the same leaf switch. But we call the rail optimized. What I mean is, so rail from the server from all the servers is connected to the same leaf. So with this, this is an efficient topology design for the SHARPv2. We'll tell you the why. So this is maximize the number of servers that can reach from each switch hop. So from this leaf switch, you can go to maximum possible number of end nodes. So this maximize the SHARP reduction capabilities, because in the multi-rail configurations, when framework can utilize it. For example, if you see let's go to the next slide. If you see the framework such as Nickel, it builds a it's something called rings. It's basically they divide the data across multiple rails, and then they do the reduction on each rail, uh, uh, each rail. So in this kind of environments, so basically, if you connect same rail to the same leaf, you can use the streaming aggregation. As I said, you can perform a limited number of streaming operations on the switch. So for the full bandwidth, let's say one streaming operation, you want to have a full resources for it. Uh, so if you connect all the rails, rail one from all the servers to the same leaf switch, so then now Nikhil can send the data, its rail data to its leaf switch. I mean, it's uh, uh, rail subtree. So similarly, each rail is connected to its a different leaf switch. They all can do the parallelly can do the different all reduction operations, and overall, you are improving the performance. Otherwise, if you push the same stream into the same stream from all the rails to the same leaf switch, so you have an inefficiency there because the bandwidth is shared across all the rails. So let's talk a little bit about the software architecture, how you can use the SHARP. So it's currently can use for. Oops, I think there is a transition.
Devender, one quick. There is a one question has been raised in the Q&A.
Okay.
It says, besides tree failure, what are the other kind of failures?
So one is mostly. So we are resources wise. We are so there is a SHARP tree. Inside a tree, there is a multiple groups. Let's assume that you can compare it as a MPI job and then many communicators. So the failure can be at the tree level, or it can be at the group level as well, at the operation level. And yeah, mostly the resources wise, the SHARP is completely independent in the switch IC level. So all the everything is tied to the tree, and then you are partitioning those resources into a SHARP group, and it can detect the errors at the multiple levels, at the operation level or group level and tree level. Tree is the maximum. I mean, if something goes at the tree level, then probably all the groups under the tree can be maybe wrong. So they maybe need to perform the cleaning operation for all the groups.
Okay, thank you.
Okay, so currently it can be used with MPI as well as deep learning frameworks. Oops. For some reason it's going. For MPI, it can be, you can directly integrate with give me a second. Let me. Oops. Yeah, some problem with this slide. Okay, so MPI, it can be, the MPI libraries can directly integrate with the SHARP. So that is which2 is doing currently now. The SHARP provides a high level API. It's very easy to use. Just it's less than 10 APIs. So you initialize the SHARP and then create the communicator, and then you post the ALLREDUCE or barrier or bcast operations. So the MWAP, which is currently is directly integrating the SHARP API. And the other approach is the HCall. HCall is a Mellanox NVIDIA collective library, MPI library, MPI collective library. So the Similarly, the way mVAP2 integrated the SHARP API HCall is also integrated to SHARP API. So now whoever uses the HCall can get the SHARP support. For example, OpenMPI, Spectrum MPI. So they have a collective component called component to enable the HCall. So through HCall, we can enable the SHARP. So for the deep learning side, so the Nikhil has a plugin to enable the SHARP. So we'll discuss a little bit more. And then, yeah, these are the ways SHARP can be enabled today. The SHARP software architecture. So what all components involved? So as I said, it's a switch technology. So we call it as an aggregation node. The green ovals that represent the switches. We're calling it as aggregation nodes, and the end compute nodes are connected to the switches through HDR Connect X6, and software components and the subnet manager. We are running a centralized service called aggregation manager. It is kind of a SHARP resource manager. Then there is a lightweight daemons running on the compute nodes. They are called SHARPd. They are only involved in the control path when we are creating the SHARP job and SHARP resources. Once that is done, while actual performing the operation, the MPI processes directly, the compute nodes directly send the data to the switches. So these daemons are not involved anymore. So they are just for setup. Then once that is done, the end nodes can use the can send the data directly to the fabric. So using SHARP with MPI. So current, as I said, it's a mVAP2. It natively integrated the SHARP, and the flag is to MV2 enable SHARP. And there are some tuning. You can find it in the user guide manuals. But yep, the OpenMPI and its flavors, the HPCX and Spectrum MPI, they integrated with the HCall. So the HCall enable SHARP is another trigger point to enable the SHARP. For streaming aggregation, the SHARP library have a flag to enable and disable, that is called SHARP call enable SAT. To if you have a HDR technology, you can experiment with the SHARP SAT. Yeah, I will leave this. Yeah, there are many tuning operations you can do. As I said, the last, previous 1-2 years in the MUG tutorials, I explained in detail about the resources, SHARP resources and tuning. You can find, if needed, if you can find those tutorials linked in the MUG site. As I said, it's a limited resources in the fabric, so you can fine tune your resources with the options. So how many, for example, if you're running a MPI job, how many communicators you want to SHARP support? I mean, for each communicator, what is the how many outstanding operations you want to post? You would like to post it to fabric. So those type of tunings you can do. And there is a tool called SHARP called dump config, which dumps all the configurations with more in detail. I just quickly ran on A1 on Selene Supercomputer just to show the full range of SAT SHARP usage for the full range of messages. So SHARPv1 was the small message optimization. For here, I ran it for 128 nodes. That is, we were calling LLT. Now there is you can use a streaming aggregation for the larger messages to have a to have a SHARP technology for a whole range of message ranges. So here that transition point is 16K. So that is where we switched from low latency tree to the streaming tree. So let's talk GPU direct RDMA. So this, I mean, you might already know it, but if somebody new to this, just have a brief introduction here. So the idea about GPU direct RDMA is that the network adapter can directly talk to the GPU. It can send and receive the data over your PCI without involving the CPU. Without GPU direct RDMA technology, in olden days, one has to copy the data from GPU to the CPU memory, and then from CPU to the NIC, from local NIC to remote NIC to the remote NIC to the remote CPU memory, from remote CPU memory to the remote GPU memory. So there are multiple hops, and it's very inefficient. It's very hard to get the full band. First of all, we are efficiently not using, and in order to get the efficient transfers in that mode, we have to pipeline properly, pipeline size, and all these were matters. So with GPU direct RDMA technology, the HCA is directly communicating with the GPU memory. So with this, it eliminates the CPU bandwidth and latency bottlenecks, and the user can do the RDMA between the GPUs. So resulting in it drastically reduces the send receive latencies and improves the bandwidth. So now we can.
Deva, that's a quick question on chat. So I think that the question is, will this work on ConnectX-5?
This the SHARP?
Yes, I believe so.
GPU
SHARP plus GPU direct. Yes.
The ConnectX-5 is only small message latency. It doesn't have a SHARPv2, so it's only low latency optimizations.
Okay, so yeah, you need ConnectX-6 or higher for SHARPv2 to work. So it's not just a switch only thing. You need a switch plus HCA.
HCA, yes.
Okay. Thanks. So any particular reason we need a switch plus HCA? Because as I understood it, SHARP was just a switch only thing.
Because the transport level protocol is different for the SHARP. Sorry, streaming aggregation.
Okay. All right. Thank you.
Mm-hmm. So now we can combine these two together, SHARP plus GPU direct. So the SHARP API today, it supports the GPU buffers as well. So it's a CUDA aware, I would say SHARP, like a CUDA aware MPI, where MPI, for example, in CUDA aware MPI, the MPI send receives can collect, API can take the GPU buffers directly. Then the MPI libraries internally can handle it efficient way. Similarly, the SHARP API is CUDA aware, and it efficiently uses the GPU direct RDMA technology. And for small LLT case, small message case, it can also use it also have a GDR copy optimizations, and the streaming you can do from the GPU memory now with the streaming with the SAT plus the SHARP. So the NVLink from on the GPUs, between the GPUs, then GPU direct RDMA to get out of the node, and then SHARP in the fabric. So this all together will create a will give you a new benefits in deep learning frameworks. So I would like to just introduce, most of the people may already know it. This is the NICL. NICL is an NVIDIA collective communication library for the GPU buffers, specifically for the GPU buffers. It doesn't work for the CPU or other cases. So yeah, it moves the data from GPU to GPU and in a very fast and an efficient way. In intranode case, it uses all the available best technologies. If it is NVLink, PCI, and shared memory based on the locality. For the scale out, it can use the sockets. But if it is IB, it uses the IB, and it can leverage all the RDMA and GPU direct RDMA and SHARP technologies. So here are some few links to download source code and binaries and perf test. So how you Nikhil will used in the deep learning world. So many frameworks like TensorFlow, PyTorch, and MXNet, and many other today are integrated with the Nikhil, because most of these frameworks
Deva?
are. Another question?
Sorry, there is another question on Q&A. Is SHARP a dedicated hardware component that is ASIC in the Mellanox switch, or is it using CPUs inside the switch for aggregation reduction operations?
It's a dedicated ASIC.
Okay, thank you.
Most of these frameworks is integrated with the Nikhil, because they're leveraging the GPU technology for the training. Like for the for the computation, CUDA libraries like CUDN and cuBLAS, the similar way, many of these frameworks are integrated with the Nikhil for the communication part. All these are using the CUDA, and underneath it's using the NVIDIA GPUs for training. A quick introduction. So why do we need? So the training, the deep learning training is a compute intensive task. You have a very big large data source, gigabytes of input data. It could be images, sound, speech, and text. You want to train the data, train your neural network. So initially you don't know anything about about it. So you give a batch of data to your network, then it will train. You have a forward step and backward step. In the forward step, you decide how wrong you are. Then you get some gradients. So what is the delta from the input, from your input parameters? So then you propagate that, correct that input parameters. Then you do it again, train your batch again. So you do it is multiple steps until you converge to a state you can recognize that images and sounds. And so this is very compute intensive. It takes weeks and multiple weeks of time to do it on a single GPU. So there is a need for a distributed deep learning, where you do the same thing on many GPUs. But now you divided your batch onto the multiple, you split the batch to multiple GPUs. So now each of them are found their local gradients, the delta from their inputs. So then you have to propagate that back to the parameter. But now you have only your local gradient. Now you have to collect that gradient across your distributed training. So for that, the operation is the ALLREDUCE, where the Nikhil and SHARP came into picture to accelerate it, to reduce the latencies of your operation, to make your training faster. So how you can use the SHARP with the Nikhil? There is a Nikhil plugin. It's an open source. You can download it from here, and it's also distributed with the HPCX. It's very simple to use. You just build your plugin and put it in a LD library path. At the Nikhil level, you just have one more option, that is a Nikhil CallNet enable one. There is another option, algorithm for CallNet, but it's not needed for anymore. Only it's for few versions. That's it. So it's transparently uses it checks if the plugin checks if the component, if the SHARP is there, if it is there, it's seamlessly uses the technology. Otherwise, it fallbacks to the traditional nickel approaches like nickel ring and nickel tree-based algorithms. So what is the advantage? So today, if you see the nickel performance ring and tree, it can already get you the speed of light bandwidth. So it can leverage full NVLink and multi-rail capabilities. So now by adding the SHARP there, so you are increasing the performance factor by 2x and 3x. This here is for the message ranges like where DL operates mostly in 8 megabytes to 256 megabytes. So the bandwidth is suddenly doubled. In fact, even we saw that it's more 2x for the message. Uh, major tree, the traditional ring algorithm, as you scale up, the number of ranks are more. The data chunk size will get small, and it's become a latency problem than more of a bandwidth problem. So the trees are not a scalable solution. This problem you can avoid a little bit with sorry, the rings is not scalable. So because it's linear, you can fix this problem a bit with the trees, where you can get to the logarithmic algorithm, but it has a here the GPU has to involve in the end-to-end computation reductions, while if it is SHARP, if the fabric is doing taking care of the computation while data is moving in the fabric at the line rate. So yeah. So just like to summarize here, yeah, it's SHARPv2 is a mix of two things, that is a low latency trees and the streaming trees. It's a optimized low latency trees compared to the SHARPv1 EDR version. It's mainly, I mean, currently we see that it's mainly main use cases is for the MPI applications, whereas streaming is achieves the higher network bandwidth and utilization to accelerate the DL applications where the data reduction sizes are in order of megabytes. So so overall, this efficient the technology, the networking computing technology, then compared to the host-based and end-based endpoint-based algorithms. Yeah, this is end of the talk. Please let me know if you have any questions. I will.
So, Deva, I had a follow-up question. So you mentioned that the protocol being used for the streaming portion of SHARP is different. Can you please elaborate on that a little?
Sure. So the low latency trees is kind of fabric holds the, I mean, the switch holds the buffers. So that means you can, the switches have a certain amount of buffer space, right? So now you can carve out that buffer space for multiple groups, I mean, and multiple operations. Let's say when you are creating a job, let's say you allocated 2 groups, and you can say that my operation size max can be message size max can be 256 bytes or 1 kilo in the SHARPv2, right? So then you can fix the you can dedicate the resources for that low latency operation, and multiple low latency operations can be do in parallel. But whereas the streaming doesn't use any buffer reserved buffer space on the switches. You are doing a kind of a inline while data is moving, right? So it's kind of a completely different technology where the HC and the switch has to need to agree upon a protocol when it has to send the next MTU message. So yeah, I sent out my MTU. Then there is a, protocol exchange kind of involved for the streaming, because it doesn't involve any storage on the switches.
Okay. Okay.
So let's simple example. Let's say one rank is entered the ALLREDUCE faster with 1 GB of message, and the other rank is not there yet. So the end node cannot send 1 GB to the switch because the other node is not there yet. So there is a there is a protocol involved to make it a in line rate, and without doing it in the line.
Okay. Okay. Sounds good. Thank you. So one other question. Like, does CodeDirect work with SHARP, or like they are two separate technologies, right?
They're completely two different technologies.
Okay.
Yeah, but the CodeDirect is the kind of revisiting some of, the core technology for the future optimizations. So, which in ConnectX 7 time, probably you might have a some more offload technologies based on that. So, but right now they are completely different.
Okay. Okay. Sounds good. Sounds good. Thank you.
So if there are no other questions, I think let's thank again Devender for this good tutorial. Okay.